This farmer can't feed his crops the way he wants. This chemical plant is vital to our food supply. This scientist thinks there could be life on an alien moon.
It's always a thrill to see an alien landscape.
The link between them all is one nitrogen atom and 3 hydrogen atoms. Ammonia. It's a poisonous gas, but it makes the food we eat. Pizza dough is made from wheat. The topping is tomatoes. Both grew on a farm somewhere. Ammonia made that happen. Smelly, poisonous ammonia keeps our world alive. And there's ammonia in space. It just might be making dinner for aliens too. Plants need raw materials like carbon, nitrogen and phosphorus to build their leaves and flowers. They get those raw materials from the air and from the soil. Good soil means big, strong plants. Today, farmers add chemicals made from ammonia to soil to make it more fertile. So they're called fertilizers. These crops help to find the best fertilizers. The fields where they grow are a huge living chemistry experiment that started 150 years ago. Back then, plant growth was a mystery. So scientists started taking samples of soil every year, searching for the magic ingredient that would make plants grow better.
Back in the 19th century, some quite bizarre materials were used, such as mummified cats brought over from Egypt, and large quantities of those were applied to land. Bones were collected and ground up and applied to the land to add phosphorus. But gradually, the modern chemical fertilizers became more easily available and a better quality too, because that's important.
This equipment analyzes water from soil. One of the key chemicals they're looking for is ammonia. To investigate soil chemistry, they deliberately don't fertilize some fields.
Well, this is a strip of winter wheat which has had no fertilizer at all for 157 years. So it's pale, there are very few plants and they're short, and it only yields about 1 ton of wheat per hectare per year.
Something's missing. This wheat isn't getting all it needs to grow.
Well, a farmer wouldn't be very pleased with this at all.
But this crop grows on soil that's received plenty of fertilizer for 157 years. It's almost perfect.
You've got lots of seeds, dark green, and the quality would be good, so a farmer would be very pleased with something like that at this time of the year.
Happy farmers, thanks to ammonia-based fertilizer. Plants and people need ammonia for its nitrogen because they're made of protein. Close up, a tiny section of protein might look like this. Hydrogen, oxygen, sometimes sulfur, but always nitrogen. All proteins contain nitrogen. The nitrogen in human protein comes from the plants we eat. And across the world, nearly half of that nitrogen came from ammonia. There's no shortage of nitrogen on Earth. More than 3/4 of the air pushing these clouds along is nitrogen. But most plants can't absorb nitrogen directly from the air. They need it combined with oxygen to make nitrate. That happens in the soil, where the plants can absorb it. But most soils don't contain enough nitrate for maximum plant growth. Fertilizer gives the soil a nitrate boost, but nitrate on its own is not enough. Nitrogen builds healthy stems and leaves. Deep underground, plants need phosphorus to make good roots. Potassium makes strong flowers. So, most fertilizers contain nitrate, phosphorus and potassium. They're called NPK fertilizers, after the chemical symbols. Ammonia is the main ingredient. Ammonia is very hard to make, even in small quantities, and the ingredients are dangerous. Nitrogen suffocates, hydrogen burns. This experiment is tricky to get right. On the left, a glass syringe containing a carefully measured amount of nitrogen gas. On the right, another syringe holding precisely 3 times as much hydrogen gas. And waiting between them, ordinary iron wool, with an extraordinary job to do. All that's missing is heat. The gases mix together as they travel back and forth over the hot iron. If it's working, this is where ammonia is created. This is the chemical reaction that should be happening here. 1 unit of nitrogen and 3 of hydrogen turn into 2 units of ammonia. The iron doesn't take part in the reaction, it's a catalyst. It helps the nitrogen and hydrogen bond together. Now it's time to find out if the experiment has worked. This pump sucks the gas out of the tubes through these yellow crystals. If there's ammonia in the apparatus, they'll change colour to blue. It works, this time. But the equation reveals why ammonia is so hard to make. The double arrows mean the reaction goes both ways. It's reversible. Ammonia can turn back into the ingredients. The trick is to make the ammonia faster than it breaks down. The human race uses nearly 150 million tons of ammonia every year. So chemical engineers have to think big. This plant makes 800 tons of ammonia every day. That's enough to fertilize 7,000 football fields. It uses a system called the Haber process. The process needs a giant maze of whining machinery and hissing pipes. It's almost all automatic, but Dick Palmer's run it for long enough to get an ear for the place.
Big machines make different noises. You can get a good idea whether they're healthy or not, particularly if you've got a lot of experience.
To make ammonia, they must first make its ingredients, hydrogen and nitrogen. This is where the nitrogen comes from. There's not much to see on the outside, but on the inside, the machinery pressurizes air to separate out nitrogen from all the other gases around us. Inside this tower, the different gases turn into liquids at different temperatures. It's called fractional distillation. Half a kilometre away is a vast furnace. It makes hydrogen from natural gas, methane. Methane has the chemical formula CH4, 1 carbon and 4 hydrogen atoms. They extract the hydrogen by mixing the methane with superheated steam, H2O, at 500 Celsius. The tremendous heat splits up the methane and the water molecules and frees up the hydrogen. What's left over is carbon monoxide. Finally, the nitrogen and hydrogen come side by side down these pipes. The heart of the plant, where ammonia is made. It's called the converter. Just like the experiment in the lab, the converter contains iron for a catalyst, and it's hot. Conditions inside the converter are so extreme that engineers very rarely venture inside. They leave it running for 2 years non-stop. But last time they went in to service it, they took a video camera with them, so we can see what it looks like inside. They had to wear breathing apparatus to protect them against the poisonous gases. Usually the converter is full of hydrogen, nitrogen and ammonia at very high temperature. And it's at such high pressure that the metal wall must be made 11 centimetres thick. Outside, enormous steel bolts hold it together. Dick uses these yellow crystals to check the converter for leaks. It's so tough that there's nothing but a tiny whiff of ammonia seeping out.
It will leak very slightly, but the leak that I detected today was well within normal limits and it's not a problem.
Nowadays, consumers don't like to think that what we eat depends on chemical plants. This gigantic machine seems a very long way from food on the table. But even organic farmers can't get away from ammonia. Pigs. Like all living things, pigs excrete waste products. That makes them natural ammonia factories. Every year, the ammonia this herd nearly 200 hot air balloons. But they don't produce that ammonia directly. Manure contains a chemical called urea, as well as compounds of ammonia called ammonium salts. As they break down, these give off ammonia. That contributes to the unmistakable smell of the farmyard. For James Black, it's the sweet smell of success.
Yes, I mean, some people find that muck has an unpleasant smell. Once it's been allowed to settle, the emissions from the heap actually tend to reduce, and there isn't a lot of smell until you come round to moving it again.
This manure is a giant natural chemical factory. A complicated chain of reactions starts turning manure into plant food. Lots of plant food.
Oh, we've got about 400 tonnes of muck just on this pad at the moment. I mean, we can fill it up more than what there is here at the moment.
In fact, the pigs make that much twice a week. Spread across the 750 hectares of the farm, it could all make excellent natural fertiliser for wheat. But the wheat can't use it directly. James depends on a long chain of natural chemical reactions to turn muck into fertiliser. The last link needs bacteria that live round some plant roots. Unfortunately, how quickly they set to work depends on things James can't control, like the weather. A hot day wakes the bacteria up and the wheat gets a nitrate feast. But if it happens to rain straight afterwards, some of the nitrate dissolves in rainwater and trickles through the soil, heading downhill. If it gets into a river or a lake, it could over-fertilise the river plants and algae. They grow out of control and it chokes the river. The effect is called eutrophication. Even if that doesn't happen, some people are worried about drinking water contaminated with nitrates. That risk is the reason why he spares muck on his farm. He can't risk spreading it.
We're having to buy in ammonia-based fertilisers rather than using the muck and slurry, of which we've got plenty, and this seems to be quite ridiculous.
But it's the law. Ammonia-based chemical fertiliser is a chemical shortcut to control chemistry down on the farm. Back at the harbour process plant, this is the control room. Outside, more than 24 kilometres of pipe. Inside, a 24-hour balancing act. Here's the problem. High pressure and cool temperature would make lots of ammonia, but it would take too long. So they have to heat the reaction up. That makes it go faster, but it also makes the ammonia break down quicker. Somewhere in between, there's an optimum, a temperature and pressure that works best. So the final stage of the plant starts with a compressor. It pressurizes a mixture of nitrogen and hydrogen gas to about 200 times atmospheric pressure. But the compression has another effect. It also forces the temperature of the gases up to about 350 Celsius. That makes the nitrogen and hydrogen gas molecules split up. Inside the converter, a hot iron catalyst is waiting for the nitrogen and hydrogen. They react together at its surface to make ammonia. The reaction also releases heat keeping the temperature just right for maximum production, about 500 Celsius. But even so, some of the nitrogen and hydrogen is still left over, so the mixture that passes out from the converter isn't pure ammonia. The very last stage chills the mixture's temperature down so that ammonia condenses out as a liquid. It's drained off from the bottom. Meanwhile, the nitrogen and hydrogen float up to the top and get sent round a loop back to the converter.
Clear to dive when swimmers are clear.
It takes extreme conditions to make ammonia, but they do happen in we're 2,000 meters down in the middle of the Atlantic Ocean. There's no sunlight here, but there is life. The fish and shrimps don't need sunlight, but they do need the nitrogen in ammonia to make protein. Lucky for them, jets of hot water from deep in the earth carry chemicals into the sea. Temperature, 300 Celsius. Pressure, about 200 atmospheres. It's much like the Haber process underwater. No wonder there's ammonia here. And if it can happen here, why not on other worlds? Away from the sun, past Earth and Mars, this is Saturn. It has a moon called Titan. There might just be alien life here. Clouds cover the surface, but space geologists are already wondering what chemistry is going on.
If I was stood on the surface of Titan in my super-duper spacesuit and was able to look around, I probably wouldn't be able to see that much because we think it's going to be fairly dark. I take a torch with me, and what I would be able to see more than likely is a kind of sludge of petroleum-like organic compounds covering the icy surface.
Under that surface, there could well be a vast ocean. Here's where alien life might exist. But to stop water freezing this far from the sun, you'd need antifreeze. And that's where ammonia comes in. Not as fertilizer, but as that antifreeze. That's Dominic's theory.
One of the things that I tried to do was explore the conditions in the ocean, availability of energy, availability of nutrients, to see whether, okay, if there is water there, could life still exist?
Dominic will never stand on the surface of Titan, but robot eyes are on their way. They might just find ammonia.
It's always a thrill to see an alien landscape, to see something completely new that no human being has ever seen before. It does something inside. It's really a big thrill.
The biggest thrill for Dominic will be to find his theory proved correct. To find ammonia on Titan, setting the scene for life.